Greetings everyone. Our paper ID is 25 and the title is Leveraging Robust CNN Architectures for Real-Time Object Recognition from Conveyor Belt. This is Noreen Tasnim Moon with the presenter ID 29 and my other authors are Sabiha Afrin Siddiqui, Shahana Parveen, Sidratul Muntaha, Mehdi Hassan, Rafid Rahman and Moin Mustaqim. This is the outline which will be covered in today's presentation. At the beginning, I would like to start with what is a conveyor belt. It is a system by which objects can be moved from one place to another with minimal effort. But sometimes an unfortunate event may occur, such as small children may get on the belt and get injured. From an article, we came to know that a 5-month-old baby boy was stuck in a Spanish airport conveyor belt, which led him to death. And in another news article, it was published that a 2-year-old boy was injured after he ended up on the Atlanta airport conveyor belt. From these incidents, we get the objectives for our research work. As to avoid these types of accidents, proper recognition of an object is very much needed. If we can recognize the objects in real time, then we may avoid these accidents and also any illegal objects. For our work, we have created a unique dataset which have been collected by us throughout the whole process of data collection and have applied YOLO version of 5 and 7, convolutional neural network model, vision transformer model, and some pre-trained models by applying transfer learning methods which includes ResNet 50, VGG 60, and MobileNet version 2. Furthermore, we have created our own dataset to be used due to a lack of complete dataset related to our field. So we have created a dataset with attributes that are connected to conveyor belt object recognition. For this, we have collected our data from 3 different perspectives, which are real-world data, basically airport environment focused, raw data from our own surroundings, and from internet sources. After collecting all images, we have filtered and sorted them to different 11 classes, which are baby, bottle, box, defect, electronics, illegal, luggage, medicine, metal, pet, and sport. We have a total of 5,741 images of different classes, which have been increased to 10,697 after annotation. We annotated all the images with the help of Maxence and then exported as per our required formats such as .txt file, .xml file, .csv file, and CocoJSON format and created the dataset to be used for the models to be trained. We have splitted our dataset into 3 categories: train, test, and valid with a ratio of 70, 20, and 10. Furthermore, for our training purpose and running the models, we have used Google Collaboratory, hence uploaded the dataset and mounted Google Drive with the Collaboratory. We divided each image by 255 for normalization after converting it to a NumPy array of float data type and further proceeded with the algorithms. Real-world data often lacks particular attribute values, thus data processing is much needed. For our work, we have read so many articles, journals which are related to our topic and have observed that they use different types of algorithms and methods to portray their claim. Here in the literature review part, we have included some of the articles from our readings. In the first paper, the author have tracked and identified objects on conveyor belts by using TOF sensor with 90% accuracy rate. In the second paper mentioned here, the authors showed a comparison between the original YOLO v5 model and their implemented or upgraded YOLO v5 model, where they ran tests using the identical set of data and got a better performance rate with 95%. After that, we have selected 2 papers which we compare with our own research paper based on field-wise and performance-wise comparison. We can see that in a paper they used the time of flight TOF sensor for identifying objects on conveyor belt and got the accuracy rate of 90%. In our research paper, we mainly used CNN architectures for identifying the object on conveyor belt and we are getting the accuracy rate of 87.7% for YOLO version 5 and 86% for MobileNet version 2. In another paper, we can observe that they used pre-trained models, their customized CNN model, and got the accuracy rate of 50%. And in our research, we also used our pre-trained, customized CNN model and got the accuracy rate of 58%, which is higher than them. However, The main contribution of our research is our own customized dataset, which includes a total of 5,741 images of different classes. Yellow version 7 was the latest and most efficient Yellow version, which we implemented or used on our research by the time of our ongoing work. We will try to upgrade the result by training on our custom dataset to predict more effectively. We have trained VIT as it can handle image data with high resolution and fine-grained tasks for our research purpose, as it is still less used in other research purposes. Now, talking about the implementations of the models and their results. Whenever it comes to real-time object detection, the first thing that comes to our mind is yellow, which is you only look once. So here we have used two versions of Yellow model, Yellow V5, which is the most popular one right now, and another latest model, Yellow V7. For the V5 model, it uses Adam Optimizer and been trained for 300 epochs, whereas the V7 model uses Adam W Optimizer and been trained for 80 epochs. We also use another object detection model, VIT, Vision Transformer model. It also uses Adam W Optimizer and been trained for 100 epochs. For the result of V5 model, it can be seen that we got really good result and accuracy, which is approximately 95%. And for the V7 model, it has been seen very pretty good result too for only 80 epochs, while on the other model, the VIT, it showed only 56% accuracy. Moreover, we have implemented three pre-trained models using transfer learning. At first, for VGG16, we have splitted our custom dataset into train test by 80/20 and provided the input image size of 150 by 150, and also weights are directly imported from ImageNet classification problem. We have set the parameter of including top layers to false as we take a trained feature extractor for transfer learning. It discards the weights of the input layer and freezes previous layers before the output layer, as we will use our own inputs and outputs. The flattened layer will take the output to one dimension. We then have the output layer, dense layer, which had the parameter of class numbers and the activation function softmax, which was used for our multi-class output. We have used Adam as optimizer and categorical cross entropy as loss function. Similarly, we have applied ResNet 50 and MobileNet, keeping the image size as 150 by 150 and by importing the weights for these models from the Keras library. We have used Image Data Generator to load the dataset, as our images are sorted and placed in the respective class or labeled folders. This method will identify classes automatically from the folder name. It also uses our model to receive new variations of the images at each epoch. We have used a global average, pooling 2D, and a dense layer with 11 as parameters for our total class number and softmax as an activation function for the output layer. Besides this, we have also tried to implement a customized CNN model where the layers were taken from the scratch. After loading the dataset, we have taken 4 convolution layers starting from the filter of 32 with the parameter of kernel size of 3 and ReLU activation function to convert all negative values to 0. The model was then trained using a fit function after compiling the model with its activation and loss function. Here we have graphs of differences between training accuracy and validation accuracy of these models. We have gotten the highest validation accuracy with MobileNet with the same custom dataset and 20 training epochs among all the pre-trained models. It has around 86% accuracy, while ResNet have 72% and VGG16 have 70% accuracy. On the other hand, we can see that we have gotten the highest training accuracy of around 95% for ResNet 50. Again, for CNN, we can see that even though our validation accuracy was comparatively low, but the training accuracy along with its prediction performance from random testing samples were quite high. Here, from the bar graph, we can see that we got the higher accuracy in MobileNet version 2 and Yellow V5, and in pie chart, the percentages have been showed as well. The lowest accuracy we got in the custom Yellow version 7 model because of lower epochs. Additionally, we have also some limitations in our research work, such as our model mainly predicts classes from random image data, so multi-class single image might affect training. Model will drop the multi-format images. For few models such as yellow, it requires high image sizes as smaller ones cannot extract the feature details. But our dataset had mixed sizes and resolution of images. The training process was comparatively slow due to using cloud environment, so we frequently got disconnected from the model training and had to restart it. When we were training on a local system, we encountered various limitations related to hardware configuration and library versions. So we had to limit the batch size for some models such as Yellow version 7. As the model training was taking a lot of time, we could not train it for a large number of epochs. For example, it is recommended to train for 500 epochs for real-time detection for a good accuracy. However, we could only train for 300 epochs as it was taking a long time. So in future, we would like to modify some things for better results. We will try to refine our dataset more. We would also try to use high-end GPU with larger VRAM so that we can overcome these limitations by increasing the image or batch sizes and epochs. As we have worked with VIT, we would like to work with some other transformer models such as DAIT, DATR. Lastly, we would like to collect real images from airport security. Here we have collected two videos from internet source and our own surroundings and tested for detection by using our models. I'm playing. We have modified some portions of our previous written paper as per the review we were instructed to do and made all the corrections. Thank you. Have a good day.